Hello, let's talk about circuits. In the previous lecture, we talked about charge, but then also we ended with talking about current, electric current. Electric current is the flow of charges. Um, it's the rate of charge flow, and that's given in amps or amperes, capital A, and that's Coulomb, which is the unit of charge per second, unit of time. So, in order to sustain the flow of charge, we need something like a water pump in a set of pipes to keep the current flowing. It needs to maintain a difference in the voltage. Sorry, that's a typo. Um, and would call this a voltage source. Um, Batteries and generators are common voltage sources. Just like how water flow in a pipe can be slowed due to an obstruction or a thinner stretch of pipe, electric current can be slowed due to resistance in the wires or in the circuit overall. Resistance depends on the materials the wires are made out of. Some materials make it easier for current to flow than others. That's a similar idea to conductors and insulators from the previous lecture. Resistance also depends on the structure of the wire. A shorter, wider wire, or whatever the object of resistance is, allows more current to flow, while a long, thin wire will allow less current to flow. And the units of resistance are ohms, and they use capital omega. That's what that symbol is. Here's a comparison between water pipes with the pump, a valve to shut it on and off, and then the line that is thinner than the rest of the pipes. Um, and then each of these elements compares to those in a circuit. So the pump and the battery work to maintain the flow of current. The switch and the valve allow us to turn off and on the flow. And the resistor and the line slow down the current. Ohm's law gives us a relationship between current, voltage, and resistance in a circuit. The current is equal to the voltage divided by the resistance. And you can rearrange this formula in a bunch of different ways to solve for each of those variables independently. But let's think about this real quick with the current. So if our voltage stays the same, but our resistance gets smaller, that would be something small on the bottom of a fraction. So that's a bigger result, bigger current. So same voltage, smaller resistance means bigger current. Or same voltage, bigger resistance means smaller current. And then if we just do the other way around, well, the current changes directly with the voltage. So the bigger the voltage is, the bigger the current, unless you're also changing the resistance at the same time. Um, if we know the resistance of this resistor and the voltage provided by the battery, we can use Ohm's law to find the current in the circuit. That's one of the things we were talking about. But if instead we know the current and the resistance, we can determine the voltage, or what is called the voltage drop, over the resistor or really any circuit element. And one way to determine that is to rearrange our equation to solve for voltage instead. And so we get that the voltage is the current times the resistance. And remember that in order for current to flow through our circuit, the battery maintains a voltage difference with high voltage on one side and low voltage on the other side. That also means that parts of the circuit in contact with those ends of the battery must have the same voltage. In this circuit, it means this side of the resistor must have high voltage, and this side of the resistor must have low voltage. High voltage, low voltage. And it means that the voltage drop over the only resistor in this circuit is equal to the voltage drop over the battery. because we have low on one side, high on the other. Same is true for the resistor. Light bulbs act as a source of resistance in a circuit also. So we have our voltage source, a switch, which remember is like the valve, it can turn it on and off, and the one light bulb. So the current flowing through this circuit is going to just equal the voltage divided by the resistance of the bulb, because we just have one thing providing resistance. But if we instead add in another identical light bulb, we have twice the resistance we had before. And because the current is the voltage divided by the resistance, we have doubled the resistance, so we've halved the current. So the current for 2 light bulbs is half of the current for 1 light bulb. What about 3? Now we have 3 times the resistance, which gives us 1/3 of the current from that we had for just 1 light bulb. This is also a series circuit. In a series circuit, there's only one path through the circuit. So the same current must pass through each element because there's no option of avoiding any elements. The resistance of the bulbs or resistors in series is the sum of the resistance of each. So 3 bulbs means 3 times the resistance. Each resistive element in the circuit produces a voltage drop determined from the current in the circuit and the resistance of that element. Again, voltage is current times resistance. The total voltage drop in a series circuit are equal to the voltage provided by the battery. So what you would find is that if we measure the voltage drop over the battery, it's going to equal to the voltage drop over each bulb added up. So this is a series circuit. And there's also parallel circuits. In a parallel circuit, current has more than one path it can take. We can see that right here. So it's coming from the battery, and then right here, currently, this switch is open, so the current can't go through this path, but it can still go through this upper path or the middle path. So it splits at this point and then recombines at this point. And obviously, if all 3 switches are closed, then it has 3 options. And a rule here is that the current, like if all 3 switches are closed, the current going into a junction, so a place where there's different wires that the current can choose from, equals the sum of each of those currents. So for example, going in, we have current current is just called I, current A, and then it splits between each of these paths, but the current through each path adds up to be the same as the current that went in. And then the same is true for the other end. Oops, sorry, this is the voltage one. For when it comes out of B, they all combine again to get the same current. Then, just like we saw before with parts of the circuit directly connected to the voltage source, having the same voltage, high on one side, low on the other, since each segment of the circuit starts and ends at the same point, so like going through any individual light bulb starts and ends at the same point, each segment has the same voltage drop. So at point A, we have high voltage, and then at point B, we have low voltage, and they're all the same. So that's telling us that each of these elements has the same voltage drop. So, rules about a parallel circuit. In a parallel circuit, the current has more than one path it can take. The current here, like I said, has 3 options to get from point A to B when all of the switches are closed. And then the current splits between each path. at point A and recombines at point B. The voltage drop is the same across each path. So voltage 1, 2, and 3 equals the voltage of the battery. And the current through each path depends on the resistance of that path. Since these, in our example, are identical light bulbs, that means they have identical resistance, so the current will be the same across all of them. But you can set things up differently with a different element in there, or maybe you put 2 light bulbs in one path, and that would change the amount of current that goes through it. Okay, so that's your introduction to circuits. Have a great day.